Hi, everybody. I'm Chris Matta. I know it says Jeff Needham outside, but I'm filling in for Jeff. I'm a senior systems engineer with Confluent. I live in Philly, so it's a pretty quick Amtrak down here. I cover a lot of the East Coast, special projects, a lot of financials, a couple of the federal stuff. I spoke here last year about microservices and Kafka. The talk today is about core concepts, becoming familiar with Kafka, understanding it. So before I get into this, anybody currently using Kafka? Okay. Anybody not know anything about Kafka whatsoever? Awesome. So, is this too loud or does it sound good? Okay, good. Good, perfect. So Kafka is an event streaming platform. Its entire job is to capture events, store them persistently, and make them available to interested parties or interested applications. Data is produced to Kafka topics and consumed from those Kafka topics. Meanwhile, it's held securely. So we've seen a ton of use across a ton of different verticals and industries. People are building microservices around it. They're using it as a security information management system. They're using it to keep caches in sync. They're using it for cloud optionality, moving data between public cloud providers and private on-prem. It's a really nice abstraction for your data, and therefore we're seeing a lot of different use cases across different industries. So hopefully I can give you an idea of why that is and what it's actually doing. So the event streaming platform has publish and subscribe semantics, very similar to an MQ system. MQ users, raise your hand. Familiar with it a little bit? Okay. Instead of just removing the message from the message queue when the consumer receives it, the Kafka cluster actually stores it and persists it. So if you're not familiar with MQ, a consumer actually have to acknowledge the receipt, and then the broker will delete it. If you want multiple consumers to get the same data, you're actually publishing multiple times, and you're creating different queues. Kafka doesn't have that issue. Since it's persisted, you can have multiple consumers actually accessing the exact same data without interrupting each other and having problems. It's distributed and fault tolerant by default, so it's built into the application layers. I'll dig into that a little bit. And it's designed to actually process these streams of data as the data moves through the cluster. So these happen typically in real time. 99% of the time, it will be a consumer reading off the topic, doing something with it, and publishing it back to the topic, happening within milliseconds of the data's creation. So we see stream processing replacing batch ETL, batch fraud. Anything you're typically doing in batch, we can probably model it in a real-time stream processing fashion with Kafka. So the thesis or the argument here is all of the data that makes up your organization, company, government, can be modeled as an event stream. All of it, right? So this is a very simple one. This is a tracking of an entity in space, right? You have, which one of these buttons is the laser point? Good. You have a timestamp, you have the ID of what you're tracking, latitude, longitude, maybe a categorization type, where it came from. This can be published in real time to Kafka, so a very easy use case for this is something like Lyft or Uber. Your phone is an entity being tracked, your GPS is being tracked, where are you, what corner are you on? The driver's car is also sending data through Kafka, and then Uber or Lyft is kind of keeping track of who's where, and when you ask for a Lyft, they figure out which car is nearby you based on real-time streams of events. Sensors are everywhere. Every single person in this room probably has a phone in their pocket. Again, it's another sensor. Wi-Fi is blanketing this space. We've got Bluetooth tracking in like retail stores now. All of these things are creating data. This data is being captured and sent through Kafka. So Audi is a customer of Confluent. They are building a connected car. So there's tons of telemetry off of all brand new Audi 2018 Audis being sent through Kafka. That data is being utilized by Audi to get a better, fuller picture of who their customers are and how these cars are being used, keep track problems that may occur in the fleet, things like that. This was the original use case for Kafka. It was capturing operational log data. So if you have a log of events, each of these lines is essentially an event in time. At LinkedIn, Kafka was developed because there were so many operational logs that they couldn't write it to Hadoop fast enough. Hadoop was not keeping up. So Kafka was designed and implemented to capture the events as a shock absorber and then deliver the data to Hadoop. So this is a very common use case. Another use case that we see in the real world, security event information management systems, operational logs across multiple organizations get captured in Kafka, enriched, categorized, filtered, delivered to different systems at different permission levels, right? So this is important. This one's a little bit wonky if you're not familiar with how databases work, but a database is actually a collection of events, right? A table is a materialization in a database, right? So in a key value store, you have keys and values. In a relational database, you have rows with different columns. But essentially what's happening inside the database is a commit log, or a binary log, or a auth log, or whatever you want to call it. It's an append-only log that is then being read by the database and materialized into tables. So in time, over time, this table can be described as a series of operations: put, update, delete, insert, etc. If we capture these events in order and replay them, we can rebuild this table in different databases. So I can capture this event log, maybe it's from an Oracle database, feed it to a Postgres database, and apply each of those events into a table. Now I'm replicating data between two separate database vendors. Kafka gets used for this all the time. So let's talk about the architecture of Kafka. What is Kafka? Kafka is a cluster of machines. This is a distributed system. What's neat about Kafka is each component that we talk about is built from data producers, data consumers, and then the brokers that hold the data. So the brokers handle partitioning, replication, fault tolerance is built into the consumer API. Concurrency is built into both the producer and the consumer API. And because it's distributed, we enjoy elastic scaling. So when I say elastic scaling, so we'll get into that in a little bit. So it's been engineered like a database. So data persistence is key and very important in Kafka. So once it's written, you want to be guaranteed that the data is there later. We can give you a time to live on your data. You can have what's called a retention period, hold the data for this long. We can order the data in a strict manner. So as it's been created in the real world, you can guarantee it's in the order in Kafka. Very, very important for financial use cases, right? If the order of a series of credits and debits is not correct, then the ledger is not right, and then this is not a useful application. What's that? Yeah, exactly. And I'll show you that here. So Kafka itself, the architecture, the abstraction, is that it is a distributed, append-only, immutable commit log. So you cannot edit any of the records once they've been inserted into Kafka. So it's, and the only way you write to Kafka is it's append-only, right? It's highly scalable. I'll borrow from Will from upstairs. So the big O notation level of work for an append-only commit log is linear. It's 1. It never, ever degrades with how much data you're putting into it because you're always just appending, right? Whereas in a database, if you're doing like an index over a B tree, the larger the index, the longer that takes, and then it's logarithmic. So we see trillions of operations per second go through Kafka, our customers and other users in the industry. This is 4 commas. This is, I think the largest one is a little over 13 or 14 million messages per second, every second of the day, every day of the year, right? The largest users are Netflix, Uber, Microsoft, which is interesting. And then I'm sure there's a number of classified users of Kafka that we can't talk about that's at this level as well. We have hundreds and hundreds of megabytes per second of throughput per broker, per node, which is, because it's distributed, linearly, horizontally scalable, right? This is an old benchmark that we like to talk about from 2014. Our CEO, Jay, before he was our CEO, was an engineer at LinkedIn, and he published this blog post called, originally the blog post was called 2 million writes per second on 3 crappy machines, but then we wrote replace crappy with cheap because we're now corporate and all that. So this wasn't even tuned. He just kind of deployed it. He didn't believe in tuning systems for benchmarks. He just wants to show it off. You can scale to many, many terabytes per server. You can build this on top. It was originally designed for commodity hardware. We have a ton of customers that also put this out in the cloud or on virtualized systems, shared infrastructure, things like that. But originally, it was designed for commodity hardware. So this is a minimal architecture for Kafka, right? So Kafka depends on a zookeeper ensemble to do leadership election, concurrency, consensus algorithms, and then configuration management for just the brokers. The brokers themselves are almost always Linux boxes or Linux instances. They organize themselves using the zookeeper. Each of them has a bit of storage, and then they organize themselves around the storage, and then you create topics on the brokers. The clients talk to all brokers at all time. So in production, you're probably going to want 5 zookeepers. A single failure on a 3-node zookeeper leaves you vulnerable for a second failure, and then you don't have consensus. So zookeeper requires an odd number or a quorum. In production, we usually see 5 zookeepers. If you get the Confluent reference architecture, we have a small and a large cluster reference architecture, kind of digs into this. Brokers are linearly or horizontally scalable. We recommend you start with 3, because 3 is a good odd number. You can get some level of durability in there, and then you can scale out horizontally. The more brokers you have, the more aggregate bandwidth the cluster provides, and the more data you can consume. And I'll dig into that real quick. I'm trying to move fast so we can see this. So this is the Confluent platform cluster. There's the zookeepers, the brokers. Then we have a number of other projects that we have. These are open source projects. The schema registry, Kafka Connect, KSQL, proxy server. These are all Confluent components. And then this is not open source, but it is our management layer. It's a web-based GUI that gives you a top-down view. So streams and topics. Data in Kafka is organized into topics. Data being published to topics is written as a key-value pair. Everything written to Kafka is a key-value pair. The key and the value, what are they? They can be anything you want. The data that, before you write to Kafka, it has to be serialized into a byte stream. Both the key is serialized into a byte stream and the value is serialized into a byte stream. That means you can literally write any data you want. Primitives, strings, numbers, Avro, CSV, XML, video, pictures, whatever you want. If you can be serialized, it can be written to Kafka. The key is an important concept, and when we write to Kafka, I'll get into that. So, like I said earlier, the only way you can write to Kafka is to append to the topic. This is a single topic with a single partition over time. This is the only way. You cannot insert in the middle. You only append, right? So these are events in the real world. Someone says, well, what if there was a bad event? Well, that's actually a real thing that happens, so you have to actually build your app around that bad event, right? You have consumers that read those events. They do not interrupt each other, right? So this is a group of consumers reading this topic. This is a separate consumer. This is a separate consumer. What's neat about this is these are 3 separate consumer groups. This is the idea here. Each of them will get a full copy of this data, right? This one has 3 consumers. Only one of them, I'll get into this in a bit, but only one of them will get the full copy. The others are standing by and waiting for that one to fail. The partitioning is where you get parallelism, and I'll show you this. Producers are also producing. You have multiple producers produce to the same partitions, same topics, same everything like that. Data is distributed around the cluster. So this is a really, really simple logical view of how the data works. This is a 4-partition topic. You specify how many partitions you want in a topic when you create it. You specify what the replication rate is when you create it. So if I have a 4-broker cluster, I've created a 4-partition topic with 1, 2, 3 copies, replication rate 3. Kafka will figure out who the leader is for each partition. It'll attempt to evenly distribute leadership across the entire cluster. Writers and readers only communicate with partition leaders. They do not talk to followers. They only talk to leaders, right? So if you see this, as a producer, you want to write to this topic, you will write to all brokers at all times. Your data will be partitioned. I'll show you how that happens in a bit. If there's a failure, an in-sync follower, one that's valid and has the data, can be elected the leader. This is what Zookeeper is doing in the background. This is a durable way to guarantee production of data doesn't stop in the face of failures. It's a durable way to guarantee consumption of data doesn't stop in the face of failures, right? You can imagine these brokers are also distributed across availability zones, right? So Kafka brokers themselves are rack aware. So if maybe this is a rack and that's a rack, et cetera, or maybe data hall aware. In Amazon, we typically produce, or we deploy brokers across the 3 availability zone regions that guarantees synchronous data replication and availability in the face of a failure, which is nice. When you produce to Kafka, you write a key. I actually don't have these slides in here, but when you produce, your key is important. The key determines which partition that piece of data is written to. It's a fairly straightforward distributed database style of data partitioning. I have a key. I run it through a modulo operation where one of the numbers is how many partitions are available for me to write to. It deterministically tells, I can deterministically tell which partition this record will always go to, right? So given 4 partitions, same key every time, it will always go to partition 0, right? That's part of how distributed data partitioning works. When you're producing, you're always speaking to the leader. A producer can have an acknowledgement setting. This is a 0 in this case. It won't care. It will just write the data. It won't look for an acknowledgement. It's like UDP style, right? You can set an acknowledgement. Ax equals 1 means it'll wait for the leader to have a copy in memory and then return the acknowledgement. Anybody see a problem with this? If the leader dies before the acknowledgement happens, you may lose data, right? Before the replication happens, right? So you can have ax equals all as a property, and the acknowledgement will return when we get copies of that data in the followers. And that's up to the producer to set. And you can see that that's the fastest and most dangerous way to write to Kafka. That's a little bit slower, but it's still pretty fast. They're all very fast. And then that's the slowest of the fastest. When we talk about millions of records per second, you can do potentially millions of records per second depending on the size of them and what your write concern is and how many brokers you're writing to and how many producers you have. This is all horizontally scalable. The min-in-sync replica piece here kind of is what happens if there's a failure of one of these, right? This is a setting on the producer. You say, well, or actually in the topic itself, you say, well, send the acknowledgement if you get 2 out of 3. If you have 5 copies, you can do submit in sync replica of 3 or whatever, so that it's an idea that how guaranteed do you want this to be? Without the new exactly once semantics, if you do x equals all and the acknowledgement fails to come back, your producer will send again, and you will get a duplicate. This is something that was built into Kafka early on. It was just like we had at least once guarantees. It was just the semantics, delivery semantics of Kafka. As of 1.0, we now have exactly once. We've borrowed some ideas from TCP/IP, where each producer gets a unique ID, and the broker keeps track of the highest sequence number of records it receives. If it sees a duplicate sequence number and producer ID, it knows that it's already got that. It sends the acknowledgement. Your producer can send as many retries as it wants, and it will not duplicate records, which is nice. So now we have exactly once semantics built into the producer of Kafka. There's some other stuff in Kafka 1, like transactional production. You can start a transaction, produce millions and millions of events, potentially over days of time, and either abort it or end it, or complete it. And that's actually one of the more interesting things. I don't know of a transactional system that can handle like transactions that last for days or millions and millions and millions of records, which is very cool. This is an older number. This max in-flight, for anybody who's a nerd who wants to like geek out on this, this is now 5. We've actually improved like 5 parallel in-flight things and still guarantee exactly once, which is good. So working with Kafka. So getting data into and out of Kafka, you have options. We have clients. This is the easiest and most primitive way to get data into Kafka. You instantiate a producer using the Java API. So Kafka, open source Kafka ships from us or from the Apache Foundation with a Java and a Scala client, and that's it. Confluent provides clients for C, C++, C#.NET, Python, Go, and there are a number of clients built on top of our C libraries, like a Node.js one from the Blizzard game company. So there's a number of these. We have support on all those. We have other ways. So there's this whole project called Kafka Connect. If you don't want to write code to write data to Kafka, you can pull a connector off the shelf, compile it, configure it, and run it. So for instance, we have a number of connectors for JDBC, S3, MongoDB. Pretty much every large database vendor has a connector. There's a number of CDC connectors. There's a project from Red Hat called Debezium. Randall actually works for us now, but he was at Red Hat when he started the project. The Golden Gate project from Oracle supports Kafka and Kafka Connect. You can use a REST proxy that we have. So if you don't want to learn the API or the native Kafka produce consume API, you can use REST verbs for that. Very simple. We do stream processing. Stream processing in Kafka does not happen at the broker in the cluster. Stream processing is happening on clients. Stream processing machines that are adjacent to the cluster. They consume data, they process it, and then they publish it back, right? There's a Java API called Kafka Streams, which allows you to simply consume data from a topic. It's literally, the Java code is like stream from, and you name your topic, and then you get a functional interface where you actually can just like map over every single record and do something to it, right? So there's a number of those in there. The neat thing, and I kind of skipped over this when I was doing produce, I didn't add the consumer group thing, and I might do that right now if you'll stand by. How much time do we have?
8 minutes.
Good. Cool. I have a consumer group slides here that can show you. Here we go. All right. So consumer groups, the Kafka API has built-in durability for consumers, right? So anybody try and write a parallel program in their life that has to do a lot of memory management and who gets what share of the work and all of that, mutexes, et cetera. It's terrible. It's horrible. The consumer API in Kafka allows a consumer to receive all of the records for a topic it's consuming from. Or you can group them together, and they will the members of the group receive a share of the work. This is two different groups, each of them receiving the same amount of data. But if we zoom into one, you'll see that there are 4 partitions. Each partition is consumed by one consumer. And they're each doing the work. They're receiving the data for that partition and committing where they are in the log. If there's a failure, so let's say this one gets partition 0, 1, 2, and 3. If the one that's consuming partition 3 is failed, Kafka will automatically pass out partition 3 to a healthy consumer. There's a heartbeat. This allows for durable consumption of data. It allows for you to build highly parallel microservices that are durable, right? So if you can imagine we have hundreds of partitions in this topic, we can have potentially hundreds of consumers per group. So the number of partitions in a Kafka topic is the atom of how parallel your workload can be for the group. Does that make sense? Anybody not understand that? So when you're designing Kafka topics, keep in mind, how parallel do you want your workload to be? You got to figure that out, and then that's how many partitions you create. So that's consumption. Working with Kafka, there's the Kafka Connect project, there's the Kafka Streams project. Confluent has a very cool project built on top of Kafka Streams called KSQL. KSQL is a way to describe streams processing using a SQL-like language, right? So essentially what's happening is we will run a KSQL service adjacent to the Kafka cluster. You'll run it yourself if you want, and you submit these queries. You can say, select star from this topic, and essentially it'll return forever because streams of data it's unbounded. So you have to hit Control-C. We can go back to that original idea of a stream of events can be rebuilt into a topic or a table. In streams, in Kafka Streams, we have this idea of a table. So you can actually apply the latest record to a materialization in the stream processor and use that as a materialized view of the table in your stream processor. This allows you to do lookups, enrichments. It allows you to do joins across multiple streams of events. You can do complex event processing. You can use the K-table to hold business rules if you want and react to them. The K-table can actually be potentially a model for machine learning. Yeah.
So that diagram, is the consumer acting as the stream processor?
In this case, this is a streams processor built on top of a consumer API. These are just other vanilla consumers. The Kafka Streams API is built on top of the vanilla consumer with a lot of domain-specific language that you can build on top of it. So if you're familiar with Spark, you're going to write a Spark thing where you instantiate a streaming context and then you map things and you do aggregates and you can do windowing. Kafka Streams has all of that built in, but it doesn't require the Spark cluster to do the coordination. So Spark is a little bit of a heavy stream processing system in that you require a Spark cluster and a master and a bunch of slaves and an operator. Kafka Streams is a Java app. Literally, it's a Java library. You can include it in your Java app. You get scalability by launching more instances of that app because it uses the consumer group. So what you're seeing is Kafka is handling the durability, the fault tolerance, the stream processing hard parts that you would probably need in a Spark cluster. Kafka handles it automatically in the API, which is very cool. So I didn't really talk too much about Confluent. I want to talk about what our offering is. It's built around Apache Kafka. Confluent employs about 80-something% of the core committers to the project. There's a couple of one or two people at different companies. I think Hortonworks has one. I think one committer. I think Cloudera has a committer. IBM has one or two. But majority of the committers of the project work for Confluent. Therefore, a lot of the roadmap and most of the innovation comes out of Confluent. So Kafka Connect, Kafka Streams, those were Confluent projects that got donated to Kafka. They were implemented and designed by Confluent employees and engineers. The Exactly Once semantics was designed by Jun Rao and the core Kafka team at Confluent. It took them like 2 years to design and build. We then ship a number of open source projects around it. The clients I talked about, the connectors I talked about, the REST proxy, the KSQL, which is new. I didn't get to talk about this a little bit. The schema registry is really important. It allows you to define what the data looks like in Kafka. Like I said, you can write anything you want to Kafka. That's a good thing. It's also a bad thing. The schema registry allows you to put some structure in there. So a topic can actually have a schema related to it. It's built on Avro. If you want to evolve your schema, it makes it pretty straightforward. And then we have some Confluent Enterprise things. Allows you to operationalize Kafka really simply. We also exist as a service in the cloud. I think we have an instance in the CI, the IC cloud in Amazon right now. We have them in Google and Amazon as well. You can come in. No, it's like a Confluent as a service. You come to us, confluent.cloud. You ask for a cluster. We give you one in 5 minutes or whatever, and then you're off and running. We run it. We do everything. You don't worry about it. You get an endpoint. You produce. You consume. That's it.
From AWS, we can consume your service somewhere.
Say?
From AWS, we can consume your service.
Yeah, and I can actually show you that here. I'll make it really simple. While I do this, partners, anybody in the room who's a integration partner or provider? We're looking for partners in the area. Confluent is very open to talking to anybody who has delivery background. So let me just do this here. Hold on. New window. So yeah, so for Confluent Cloud, you can go to confluent.cloud. You can create a cluster, name it, figure out how much speed you want in and out. Like, you want to go high, low, whatever. How much storage do you want? And it'll, I'm having trouble like targeting this. You can say, you know, that's your hourly rate right now. There's an Amazon rate and a Google rate. Google's cheaper. There's a nice discount with Google right now because we're partners with them. So Confluent in the cloud is really useful for kicking the tires, figuring it out, learning about it. We have, this is a professional version. We have an enterprise version which we can handle and manage your full SLA workload. So we have very large customers for that. So. We have T-shirts. If anybody wants T-shirts. Something before I go, I have to talk about my shirt. We have customers that love Kafka so much. This was an internal T-shirt made for a hackathon at Royal Bank of Canada, where they talk about the 3 greatest inventions of mankind as fire, the wheel, and Apache Kafka. So this was available to internal people. I was their sales engineer and was running their hackathon, so they gave me this one. We're very excited about the project. I have cards up here, and I have Confluent takeaways as well. How much time do we have? Do we have any questions time?
Yeah.
Go ahead.
Any encryption or encryption for that reading, writing, encryption?
Yeah, so the question was, is the data encrypted? Yeah, so you can have end-to-end, you can do TLS encryption between clients and brokers. Brokers communicate over TLS. All of that is totally encrypted. By default in the cloud, it's all encrypted that way over SSL. It adds a little bit of overhead in CPU, but it's not so much that, because Kafka's not typically CPU bound, so it adds a little bit of a CPU overhead on the brokers. You can also implement end-to-end encryption. Remember, you can write anything to a Kafka topic, so we have customers that are actually encrypting payloads at the producer and decrypting them at the consumer. So you can do that out of band as well.
Compression.
Yeah, you can do, there's 5 different libraries we support, gzip, LZ4, et cetera. You identify it, the brokers handle it. Yep. You can do encryption at rest as well. So it's a Linux service. You can use Vormetric or whatever, EBS encrypted volumes. This is going to be, if you deploy this will be in EBS encrypted volumes as well. Yep.
On the back end, you store data in AWS, you store in S3?
No, it's all the data stored in Kafka is in a Linux file system, ext4 or XFS, or if you're really wild, you can do ZFS. So it's like each node has a copy of the data in its file system. It's not using HDFS. It's not using a shared file system at all. This is how we can do. Yeah, total block storage, local to the drive, to the system. We can do trillions of events per second because each node is doing hundreds of megabytes. The only way to really do that is local storage.
Since we have like equivalent stores underneath, so does it mean that you guys have your own management system, or are you using something underneath, like whatever?
We're using the Linux file system. Literally, the data is written into the page cache, and then it's persisted to disk using that. A topic is a directory. So a topic is a number of directories. A topic is made of partitions. Each partition is a directory on the Linux file system. It's extremely straightforward architecture. We feel that simplicity is. The record is just a byte stream. So it's in the page cache. There's a series of bytes. That page cache is now written to disk as pages, and there are index files that sort of index it. It's really, really easy. It's not a key value store. It has keys and values, the records, but it's not. You cannot do a random lookup of an index. We're not indexing the keys except in time, in the order they were written. That's the only index we have. The key is important to the partitioning. Yes, exactly right. And the order, potentially. Yes, exactly right. Sharding is the right way to. We're standing on the shoulders of distributed giants at this point with this. Same stuff, right?